of Miami and CINVESTAV as well. And he's going to talk about the category of superalmiares.
Thank you. Thank you very much for the invitation. My talk is more conceptual rather than technical one. Then I will talk about category of superalmiares. Okay. Okay, this is the outline. First the motivation, then we will introduce the category of pajares, then the category of pájaros, then the category of almiares, and finally I will show a Euclidean reduction of these concepts. Okay, the aim of this work is to provide a convenient theoretical framework to model the moduli space of Riemann surfaces as Witten and Donaghy work. Then I will take the conceptual problem introducing a categorical language to organize local information as an alternative to the well-known descent theory. Okay. Let's start with a very simple fact about Lie groups. A Lie group is a group object in the category of manifolds. In this case, you have a manifold. You can think in the functor of points of the manifold, and if the functor of points leads to the group category, then the manifold has a Lie group structure. Okay, here is a manifold, the opposite category of manifolds. Okay, then this is a presheave. Then if the functor of points of manifold leads to the category of groups, then the manifold has a Lie group structure. It's a basic fact of category theory. Okay. Now, we introduce a category of these objects, these functors, from manifold to groups, and we will say, in fact, we work with
the
this.
The category of the top is the category of discrete groups.
This is the category of groups, is discrete category. Okay, and we will to work with the functor of points of the manifold. We want to work with presheaves from manifolds to sets. Then we introduce a definition. If you have a presheave from manifolds to sets, we will say that F is a pajar if there is a functor from manifolds to groups such that this diagram commutes. Okay, if F leads to groups through a functor from manifolds to groups, then we will say that F is a pajar. Okay, then let's now start to prove that the pajares are a category, and the morphism are natural transformation between them. Okay. Also, it's clear that the pajares that are representable by the Joneda's lemma turn out to be a full subcategory of manifolds. Then the first theorem is that the category of Lie groups is equivalent to the category of representable pajares. We have a picture of the E8 Lie group. The E8 Lie group is a group that appears in some physical theories, and this corresponds to a pajar. Pajar in Spanish is the word for, in English, stack. Stack is the same in Spanish as pajares. Okay, this relation, the groups are equivalent to some type of functors that leads to the category of groups be extended to the category of groupoids. A groupoid is a small category where each morphism is invertible. Denote by G sub 0 and G sub 1 the set of objects and the set of morphisms respectively. Then we have a collection of morphism, structural morphism, composition, target. This is instead T is S, it's a source and target map, a unit map and an inverse map. This is the fiber product. This fiber product is defined as this set. Okay, and the map M, the composition is defined as S composed by 1. Okay. A Lie groupoid is a groupoid where the objects and the morphisms are smooth manifolds. And the source and target map are surjective submersions. As a consequence, we have that this fiber product is a smooth manifold. And the map, the composition map, is smooth. Also, the unit map and the inverse map are smooth. Okay, with this in mind, we will introduce the category of pajaroids. This is an analog concept to pajares. We have pajaroids. Okay, and again, let C is male category, F functor from this category C to groupoids, and naturally there exists a pair of functors, objects, and we have forgetful functors from groupoids to set that forget the morphism and the object respectively. Okay, we will say that the functor, this functor F, is representable if there exist objects in C, the category C, such that this composition are representable by such objects, C sub 0 and C sub 1 respectively. Okay, then first theorem is that if you have a representable presheave whose representative objects are manifolds G sub 0 and G sub 1, then if F leads to groupoids, draw a functor from manifolds to groupoids, presheave, then a G sub 1, G sub 0 are the morphisms and the objects of a Lie groupoid. Okay, then it's completely similar to the result for Lie groups. This sketch of the proof is a general proof for many results of the same type. You have the functor, in this case F. F is a presheave from manifolds to sets, and this F hat is the lifting of F. Then to get that the maps are smooth, we have that observe that this diagram is commutative. Okay, then for example, we can take a point X, and a point induces in a natural way a map X. A map from a point to a manifold is the same as a point in the manifold. Then we have a natural map X that represents a point in G sub 1, for example. Then this diagram is commutative. Then we have these equations. Okay. Also, from this diagram, the unit map, the source and target map, we have that the source composed by the unit map is the identity, and the tangent, the space of m sub 0. In this case is, sorry, this instead m, instead m is g. Sorry, is g. G sub 0, g sub 1, g sub 0. This is g sub 0. And we have that this composition is the identity, the composition of the differentials of these maps or the identity. From this, it follows that this fiber product, if this is M1 and M1 is a manifold. Okay. Well. Okay. This diagram permits us to prove that the composition map is smooth. Okay. From the commutative of this diagram, we can take three maps that represent 3 points in the manifold that represent the morphism. Again, this is not this M is G1. This is G1, G1, and G1. We have X, Y, and Z are maps from a point to G1. Okay, and this diagram commutes, and from this we conclude that the composition is a smooth map. A similar argument, again by a commutative diagram, show us that the inverse map is also smooth. Again, this G1 and G1. I'm sorry. Okay. Well, the previous result suggests the following definition. If you have a presheave, we will say that F is a pacharoid if this functor leads to groupoids. Okay, it means that there exists an extension from manifolds to groupoids, such as this diagram commutes. Okay. Well, again, the collection of pacharoids together with natural transformations between them forms a category called pacharoids, and we'll denote it by PJD. Okay, this is the picture shows Claude Monet as this almiare. This is okay. We have previously we have pacharoids, and with the pacharoids we can define a new objects that are the almiares. Almiares is the quotient category of pacharoids modulo natural isomorphism, and this means that an object of this new category is an equivalence class of under isomorphism of pacharoids. Well, results that almiares is deeply related with C infinity stacks, with differentiable stacks. A differentiable stack is a groupoid value shift on manifolds. This is a very short definition. Really, it's a very technical one. It's a very technical definition because I need to write different conditions, local conditions that permit us to glue in another objects and construct a global one. Okay. As I mentioned, differentiable stacks and almiares are deeply related, as observed the following theorem. Results that the category of C infinity stacks is equivalent to the category of almiares. Then there is a interesting advantage in terms of the definition, because C infinity stacks needs decent condition to work. Then in the case of almiares, only we need to check if some functors lift to the right category. Okay, then the theorem is that the C infinity stacks is equivalent to almiares. Okay, The idea of the proof of this result is that there exists two functors. The stackification functor that given a Lie groupoid or a groupoid in the general case to construct an associated stack. This stack is defined as follows. If you have a manifold Y, the quotient stack associates to Y a principal G bundle, and also there exists a groupoidization functor. If you have a stack, in this case a differential stack, then you can take a chart, and you can construct a groupoid. The groupoid is you can construct this fiber product, and you have a natural source and target maps, and it's not difficult to prove that these pair of functors give us an equivalence. In this case, the equivalence is that the quotient category of the differential stacks is equivalent to almiares. Okay, this idea, you pick up element of almiares, in this case, almiares that are representable, and you pick up two elements in this class. These elements are represented by these two Lie groupoids. Okay, and a well-known fact is that if this groupoids satisfies this equivalence, the quotient stack associated to this groupoid and the quotient stack associated to this groupoid are naturally isomorphic. Then, with this argument, we can prove that the quotient category of differential stacks modulo isomorphism is equivalent to almiares. But this quotient category, in fact, is equivalent to the category of differential stacks, because this is a skeletal category respect to differential stacks. Okay. Okay. Well, an important result that is a test of this concept, of this theory, is we have a notion of the strong Morita equivalence of Lie groupoids. Okay. Then you have two Lie groupoids, G and H, and a morphism of Lie groupoids. We will say that this morphism is a strong Morita equivalence if this composition is a surjective submersion, and this diagram is a Cartesian square. Okay, this is a definition of strong Morita equivalence between Lie groupoids. Then this result again shows the advantage to consider lifting functors to organize the information that provides the descent theory. You have two Lie groupoids, then there is a bijection between natural isomorphism between the lifting functors and the strong Morita equivalence between the Lie groupoids. Okay, then you have A, H, and J Lie groupoids, then has an associated functors F sub H and F sub J, and if you have a natural isomorphism, this implies the existence of a strong Morita equivalence between the Lie groupoids. And also, if you have a strong Morita equivalence, this implies the existence of a natural isomorphism between these two functors. Okay, the sketch of the proof is not difficult to prove this theorem. Okay, we have a natural isomorphism. Okay, we need to produce a strong Morita equivalence. Okay, and this is the argument that permits us to construct such equivalence. Okay, suppose that you have manifold, and for this manifold we have this map induced by the natural isomorphism, and naturally this map has associated two maps, objects and morphisms, and these maps commutes with all structural maps. Okay, this is F cursive font commute with all structural maps. In our case, we have that this object is exactly the functor of points of gy, gives of 1, evaluated in the manifold X. And this object is exactly the functor points of H1 evaluated in the manifold X. By hypothesis, these functors live to the groupoids. Then okay, groupoids. Then if we consider a point as a manifold, 0 dimension, then we obtain a map from G1 to H1. And by the general lemma, we deduce that this map is smooth. Okay. Well, this map naturally induces a map in objects. If we take psi sub 0 as this map, then we get a map between objects. Okay, it's for each x in the manifold X. Since this is a natural isomorphism, size is a natural isomorphism, then we get ejection. This case is a ejection. This morphing is a ejection for its manifold X. Then the induced map psi sub 0 is surjective, and the map psi sub 1 is injective. Moreover, it is not hard to prove that these morphisms are psi sub 0 is a submersion, and psi sub 1 is an immersion. Okay, now from this diagram, we can obtain that this map is a surjective submersion. Okay, it's difficult to prove because we have that this map is a surjective submersion, and this composition automatically is a surjective submersion. Okay. 2 minutes. Sorry. Okay. Well, this is the construction. This is the argument that proves that we have a Cartesian square, and we can construct the fiber product, and this argument proves that satisfies the condition for a Cartesian square. Okay. Let's see the argument. More. Okay. Well, the previous arguments could be extended to the supersetting world. We have also a notion of superalmiares. Superalmiares is defined in similar form as a pajar. Instead, the manifold category of manifolds, we have the category of supermanifolds. And we have the same picture. If you have a functor that lives to the category of groups by a functor f from supermanifold subgroups, and you have here the functor that forget the morphism. Then we have, in the case of f is a representable functor by a manifold that a supermanifold that the representative supermanifold is a super Lie groupoid. Super Lie group, sorry. Okay, we have a similar theorem. Lie supergroups is equivalent to representable superpajares. The argument is very similar. Okay, and again, this is a trivial fact. Is the notion group object in the category of supermanifolds. Last, again, same structures, but now in supermanifolds. Okay, and again we have the notion of superalmiares as the quotient category of pajaroids modulo natural isomorphism. And unimportant results are that in all these diagrams we have the category of manifolds of supermanifolds, but we can work with a smaller category. We can use categories, Euclidean categories. Okay, we don't need the manifolds or supermanifolds. We only need categories with less objects. In this case, Euclidean categories. For example, in the case of manifolds, Euclidean category on R, its objects are open sets and some Euclidean space, and the morphism are smooth maps. And in the case of super Euclidean category on R, the objects are superdomains, and these are ringed spaces where you use an open set in some Euclidean space, and this is a structure shift that is locally isomorphic to this shift, the smooth function tensor, the exterior algebra. Okay, and we have these reductions. If you have a functor from the category, Euclidean category, to sets is a presheaves, and this F leads to the category of groups, then there exists an extension from manifold. This is manifold. This up of manifold. There is extension F sharp, such that F sharp restricted to this category is exactly F. Then we don't need manifolds, only Euclidean category. The same for groupoids. If you have this functor, and this functor leads to groupoids, and there exists an extension from manifolds to set, so the others restricted to this category is SF. Also in the super case, you have this Euclidean category, super domains, and you have a presheaves that leads to groupoids, then there exists an extension to manifolds. So this is the idea, how to construct it. The extension is inductive. The proof is inductive. We need to take an inverse limit. Okay. First, we take these five products, the intersection of these objects in the category, Euclidean category, and these objects, these five products, are constructed by inclusions. And this is the first step. The second step is to consider the open sets, U sub alpha, and we can construct these two sets, E sub 0, or the image of the functor f hat over these open sets, and E1 is or the set of image of f hat over this element, so U1, and E2 is defined as a fiber product, and this inevitable definition gives us an inverse system of groupoids. And if we take the inverse limit, we have F sharp. Okay. Well, with these results, we can define a convenient notion of super overfold. Overfold is a groupoid where the stabilizer group is discrete for each element, for each object of the Lie group, groupoid. And the map from the morphism to this product is proper. It's a proper map. Okay, morphable structure is a pair of a map of homomorphism from the orbit space of groupoid to X, and the groupoid is a orbifold groupoid. Finally, orbifold is a triple topological space X, orbifold groupoid, and a homomorphism formed from X to the space of the orbits of the groupoid. There is well-known facts about the groupoids and orbifold groupoids. For example, this one is you have a Lie groupoid, then the stabilizer is finite for each X if and only if the arrows from, or the morphism from X to Y is finite for each X and Y is sub 0. Well, we have an equivalence Lie groupoid. G is an orbifold groupoid if and only if the stabilizer is finite for each object in the groupoid. Well, with these notions, we have a definition of a superorbifold. A superorbifold is a superalmiare representable, and for each point, the superalmiare in this point, for each object in this set, the stabilizer is finite. It's not difficult to prove that this collection of superalmiares with this property is a category, and this is the category of superorbitals. And I'm sorry because I'm so nervous. Got little time. Okay. Thank you.
So, one question. We thank the speaker again. So we